Hey everyone, in this video we're going to be talking about rolling contact bearings and specifically looking at examples of finding bearings from a catalog based on desired criteria. And this video is part of a lecture series on mechanical design 2. And what we're going to do is we're going to do a couple of example problems based on the book Shigley's Mechanical Design, and specifically some problems associated with chapter 11. So we're going to start with this first problem, problem 11.3, that says that an angular contact inner ring rotating 02 series ball bearing is required for an application in which life requirement is 40 kh, which is kilo hours, at 520 RPM. The design radial load is 725 pound force, and the application factor is 1.4. The reliability goal is 0.9, and we're asked to find the multiple of rating life XD required in the catalog rating C10 with which to enter table 11.2. Choose a bearing and estimate the existing reliability in service. So a pretty complete problem with a lot of things to do. And we have table 11.2 that's given to us. And you can see that 11.2 has some information with bore, outer diameter, width, and then deep groove and angular contact values. And what we're going to be interested in this table is our C10 values, to find our C10 values according to the question. So let's start with this question and let's read the problem and go through, and you can have the problem out as a companion to this video if you want to, but we're going to read through the problem and kind of add all of the different factors. Now, I'm going to add all the different factors and I'm going to write them down as if it were in the problem. So there's a couple of things that we need to know, is that it's a 02 series, which we'll look at later, but it's important just to know about and to make sure that we have that series number. We also have angular contact and inner ring rotating, which might not be completely important right now, but is going to be important later on in this module at least. Okay, so angular contact is going to be important because it's going to make us choose to look at this value, and we know it's not going to be a deep groove. So that's one thing already. Then we're told that the life requirement is 40 kilo hours at 520 RPM. So we can write that L sub D is going to be this much. So this is our life desired. Then this is going to be our force desired. And then this is going to be our application factor, and our goal reliability is 0.9. Okay, so we're going to write all this down, and then we're going to solve the problem, and we're going to find XD first, or X desired first. Okay, so we start off with, and we go ahead and write down all the information from our problem. So we can say that AF is equal to 1.4. That's the application factor, or in other words, the safety factor. We know that our reliability desired is 0.9, which is going to simplify our problem a little bit, and we'll see how. Then our life desired in hours is going to be equal to 40,000 hours. Okay, so that's 40 kilo hours. Then we have that N is 520 RPM, given in the problem, and our force desired is equal to 520 RPM. Is equal to 725 pound force. So based on this, we are told we have to find XD and we have to find C10. Okay, so the first thing that we can find is XD, and XD, you can look this up in your formula sheet, or you should remember it off the top of your head, is life desired over life rated, or life 10, okay? And in our case, we have our life desired in hours and RPM, so we can convert from hours and RPM to revolutions. So we can say that it's 60 times LDN divided by LR, okay? And we know that our LR is always equal to usually 10 to the 6th. That's the usual rated life, or the life rated for any bearing that we're going to see in this application. So we can write this out and then we can plug in our numbers. And if we plug in our numbers, we get that XD is going to be equal to 1248. So that means that the life desired is 1248 times higher than 10 to the 6th. Okay, then our next step is, according to the problem, is to find the catalog rating with which to enter table 11.2. So we're not looking for a catalog rating specifically for table 11.2. What we're looking for is a C10 value, based on the problem that we have and based on the desires that we have. So now what we're going to do is we're going to go look at what equation we can use for C10. And this is not very tricky per se, but you do have to choose the right equation, although all equations could work specifically for this problem. For other problems, some equations might not work. So the first equation that's the simplest is this C10 equation is equal to FR is equal to FD LD over LR to the 1 over A. And we see that this equation is valid for R is equal to 0.9. So we could use this equation and just solve this equation directly. And the reason we can do that is because we essentially have our proof that if we're on a graph of log f versus log of life or log of x, we would have a straight line, and we are on that r is equal to 0.9 line where we've developed our equations. So we could use that equation directly. Now, the other equations we could use are this one, which is valid for any reliability. So it's valid for 0.9, it's also valid for 0.95, 0.99, 0.8, whatever it is. And then this is valid for 0.9 or higher. So this one would also be valid. Now, what I want to do just to illustrate is to say, well, we're going to obviously use this equation because it's the simplest one. But what would happen if we actually wrote down this equation instead? Okay, why is it that those two equations can be used for 0.9? Well, it's possible because this part of the term, and I'll highlight it in yellow, this whole part here is actually, when you use 0.9 into here, this is actually equal to approximately 1. So it simplifies to just XD. Okay, and remember, XD is equal to LD over LR. Okay, so essentially what happens is this bottom part is equal to 1, so we're just left with AF times FD XD to the 1 over A. Okay, so you could use any equation in this case, but obviously we're going to use the simplest equation, which is the first one in this case. Okay, if you have a reliability that is not 0.9 or a reliability goal that is different than 0.9, you would have to use either the middle equation or the bottom equation. It's up to you which one you want to use, as long as RD is greater than 0.9. Okay, so hopefully that made sense, and we'll keep going with our problem. So what we're going to do is we're going to write that C10 is equal to 1.4, which is your AF, times your FD, which is 725 pound force, multiplied by XD, or LD over LR, but we already have that value, so I'm just going to write XD to the power of 1 over 3. We have a ball bearing, so we're going to use 3, not 10 over 3. Okay, so this is because we have a ball bearing. So based on this, we can then say that our C10 value is going to be equal, and C10 is going to be in pound force, is going to be equal to 10,927.9 pound force. So although we have a requirement of force desired of 725 pound force, because we are running the bearing for so long, and because we're running it 1248 times longer, we end up with a very high number for the pound force, because we want to basically, we want to essentially have a much higher force resistance if we're only going to be running it for 10 to the 6th. Okay, so our catalog value is that value specifically, or 10,927.9 pound force. Now, the next thing we're going to do is, because we have this C10 value, now we can go back to our problem and see what's required. Okay, so we have that in our problem, it says that we need to enter table 11.2, and we need to somehow solve for a certain load rating that we can use and choose a bearing. So in order to choose a bearing, what we're going to do is we're going to go into this table and try and figure out what bearing could work based on our value of C10 versus the value of C10 that we have in our problem. So in order to come up with that, what we need to do is we need to convert our pound force to kilonewtons first, because the table is in kilonewtons. So what we're going to do is we're going to do 10,927.9, and we're going to convert to kilonewtons, to newtons first, which is multiplied by 4.45. That's the conversion factor. You can also use a conversion online as well. It's 4.448 usually, but we'll just use 4.45, which gives you 48,629 newtons, which simplifies to 48.6 kilonewtons. So we know that our C10 value in our catalog should be 48.6 kilonewtons. Now, if we go to our catalog, we're going to see that we don't have an exact value of 48.6. So pause the video here and try and think what we could do in terms of coming up with a value of C10 that is appropriate and choosing the right bearing. So if we look at our table, we have these two bearings are very close, so I'll highlight the lines. Okay, so it's these two lines that are very close to our value of 48.6 kilonewtons. Now, in order to make our problem work, what we're going to do is we're going to pick the number, we're going to round up to the next number. We're going to make sure that we have a safe environment and that we have at least a reliability of 0.9, so we're going to go with the value that is higher out of the two. We're not going to go with a lower value than 48.6. So 48.6 is kind of our minimum value. And what I'll do here is I'll check the one that we're going to pick. So we're going to pick the bearing with a bore of 60 millimeters. So we can say that in order to satisfy our problem, we're going to choose the 60 millimeter bore. And once we've chosen the 60 millimeter bore, we're then told to find one last thing. It tells us, for the last part of the problem, it tells us to estimate the existing reliability in service. So now, since we've chosen a value of C10 that is slightly different than 48.6 kilonewtons, it's higher, we can actually come up with a reliability number for that C10 chosen. Okay? So what we're going to do is we're essentially going to measure the reliability that we would have as opposed to our reliability goal. Now, because the C10 is slightly higher, we're going to assume, and it should be a fair assumption, that reliability should be higher than 0.9 because we've chosen a bearing that is stronger than what we actually needed. So what we can do is we can solve for R based on the equations for R that we have in our formula sheet. So if we go to our formula sheet, we can go back to Module 3 formula sheet, and we see that we have two equations here. We have R is equal to exponent of minus xd, etc., 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 or we have a simplified version. So we have these two equations, 1 and 2. We can use either equation. The first equation is always right. The second equation is correct for R is greater than 0.90, so we can use either or. If you do have a calculator, I suggest you just use the more accurate one, which is the one with the exponent, and then you just solve the equation and you put your values in. So let's put some values in associated with our associated with our problem. So going back to our r, we have that r is equal to exponent, and I'll write inside the bracket in black, so we have minus 1248 multiplied by 4.52 kilonewtons divided by 55.9 kilonewtons, all cubed, minus 0.02, all divided by 4.459 minus 0.02. And you can go back to the formula sheet if you want to see what those values are. All to the power of 1.483, close brackets. Let me make that close bracket in red so that it matches the other one. And we get that if we solve the problem, we get that r is equal to 0.945. So what we're saying essentially is that our reliability, if we choose the 60 millimeter bore, is actually going to be, even though our desire was 0.9, our actual reliability in service is going to be 0.945. Okay, so we're now going to do a second example problem that uses a slightly, we just have to find C10, and we'll go look and solve this other problem. So I'm going to copy over this problem 1110. Okay, so I'll copy it over into our notes here so that we can read it and go ahead and understand what it's asking. Okay, so we have the following problem. So it says, for the bearing application specifications given in the table for this specific problem, determine the basic load rating for a ball bearing with which to enter a bearing catalog of manufacturer 2 in table 11.6. So there's another table with which to enter, but in this case, we just need to determine the basic load rating for a ball bearing, okay? And what we mean by basic load rating is just our C10 value. And what you can do is you can go through and actually solve this problem for every single problem. So you see there's 1110, 1111, 1112, 1113, 1114, and 15. You can try and go ahead and solve this for every problem. Now, I'll just do the first one just so that you can see what's happening. So we would start with, for 1110, we would have the first problem, and we could say find C10, which is your basic load rating. Okay, so your basic load rating is C10. And if you had 1110, we have a desired reliability of 90%. We have a design life of 10 to the 9 revs, and we have a radial load of T kilonewtons. So what we can do is we can go to our equation to find C10, and since we have a reliability of 90%, we can use a simplified equation. Okay, the first equation within our formula sheet. And we know the application factor is 1, so we would just have 2 times 10 to the 9 over 10 to the 6, all to the power of 1/3 because we have a ball bearing. And our C10 would therefore be equal to 20 kilonewtons based on our problem. And you can repeat this for the other problems. If you have a desired reliability that's other than 90%, you would use the long form of the equation. So you would go back to your formula sheet and you would use either this equation. So let me erase some of the things here so that we don't get confused. But you would essentially use either this equation or this equation to solve for those values. So for higher than 90%, you could use either the second equation or the third equation directly. Now, the one other thing that we have in this problem that is of note and is something that we need to write down just to make sure is that we have a rating life, and we're told that in this case, we have a catalog of manufacturer 2. Okay, and typically in this lecture series and in this module, we're always going to assume that we have manufacturer 2. But there could be some problems that you might be faced with where you have a different manufacturers with a different rating life. So you can see that manufacturer 1, for example, has different Weibull parameters to be used. So instead of using x0 of 0.02, 4.459, and 1.483, which is what we've used so far for our analysis, you could have a different manufacturer that has different values of x0, theta, and b. And you can see their rating life is also different. So that means that their LR would be different as well. So if you had this question based on manufacturer one, you could have potential differences in your answers. Now, what we're going to do is throughout this lecture series, we're going to try and stick with manufacturer two, and with a rating life of just 10 to the 6th, with the Weibull parameters given. So this is a good practice whenever you're solving for problems 11, 13, 11, 14, and 15. You'll see that you can use your manufacturer two Weibull parameters within that equation, which is also the ones that are given in your formula sheet. So we'll stop it here for this part and this video. In the next video, we're going to look at combined thrust and axial loading. So we'll see that there's not just axial loading, there's also, well, there's not only radial loading, there's also axial loading on your systems. So we'll look into that and how we can solve for problems with two different types of loadings on our bearings. So we'll see you in the next one.